Hi, I am Akshay Raj. In this video, we are going to discuss about what is internal flux linkage of a conductor in a transmission line. For this analysis, we need to consider a conductor of radius r and it is having a unit length of 1 meter, and we need to consider a cylindrical portion of this conductor for this analysis to determine the internal flux linkage of this conductor. Let dx be the differential length which is x meters away from the center of this conductor, and d phi be the flux that is flowing through this fractional portion of that part that we have considered, and hx be the magnetization force that is produced due to the flow of ix current. This ix current is responsible for the production of this magnetization force hx. And remember all these points whatever I have said, that is L be the 1 meter and R is the radius of conductor, and dx is x centimeters away from the center of this conductor. Hx is magnetization force that is produced because of the flow of ix current, and d phi will be the flux that is present in this fractional portion. My dear friends, listen very carefully. For the analysis of total internal flux linkage that is going to happen within this conductor, we will consider what is the flux linkage that is going to happen within this fractional portion that we have considered. For that analysis, we need to consider what is the flux density that is going to happen within this fractional portion, and by using that flux density we will try to analyze what is the flux d phi available within this fractional portion, and we will use this phi in general equation of flux linkage, that is psi is equals to n phi. So within our syllabus that psi is denoted as lambda, so that consider lambda is equals to n phi. So our only responsibility is about to determine the d phi value. If this d phi value is available for that, then it is very easy to determine the total internal flux linkage that is going to happen within this conductor. That's it. Coming to the derivation part of this lecture, firstly we need to find what is this hx, and this hx can be determined by using circuital law. Circuital law states that the current flowing through the conductor is equal to the line integration of the magnetization force. That is, we are considering ix current is flowing through this particular cylindrical portion. Therefore, ix is equals to integration of hx dx, and the limits are from 0 to 2 pi x. If we integrate this, means ix is equals to hx integration over 0 to 2 pi x dx. Now this will become hx into x, and the limits are 0 to 2 pi x. Now this will become hx 2 pi x. Now hx is equals to ix divided by 2 pi x. First part is completed. Now we need to determine what is the flux density over this portion, that is bx. So we have a formula for this, that is mu hx, and this mu is equals to mu naught mu r, and the value of this mu r is equals to 1 if we consider the medium as air. Therefore bx is equals to mu naught hx. Now substitute whatever you have got now over here. bx is equals to mu naught hx is equals to ix divided by 2 pi x. Now we need to determine the differential flux that is happening in this portion, that is d phi is equals to bx into a. If you are a diploma candidate, you are capable of determining this formula, like flux density B is equals to flux upon an area phi by a. If you subject this phi, we will get phi is equals to B into a. This is what I have written over here, and the flux is d phi, flux density is bx, and a is the area. Now this d phi is equals to substitute whatever you have got recently over here, the value of bx, mu naught ix divided by 2 pi x. A is the area. So we need to consider the total flux over the unit length, not only about this area, this cross section area. This is of dx length. Let us consider this as breadth, and the area should be L into B, like L into B. This will be the breadth, and we need to take through the conductor 1 meter length of conductor, so that L will be 1. Generally, we know that area is equals to L into B for a rectangle. Let us consider my pen as a conductor, and I need the total flux that is happening within this total area over the length of this conductor. My dx portion will be like this, that fractional portion over here over my pen, and I need the unit length, whole length d phi over this pen, so that this A will become this distance. This will be like breadth dx into my whole length will be 1. Why? Because I considered unit length, that is 1. Now d phi is equals to mu naught Ix divided by 2 pi x into dx. Here try to write this Ix in terms of phi. So how we can write that means, if we neglect the skin effect within this conductor, then the flux density at any point will be equal. Therefore, flux density Jx at this portion is equals to flux density, that is Jx is equals to Ix by 2 pi x, that is equals to I by 2 pi r. Current over an area, pi x square, pi r square. Now subject this Ix is equals to x square by r square into I. Now substitute this Ix over here, therefore you will get mu naught Ix square divided by 2 pi x r square. Here this one and this one will get cancelled. Now we need to consider the flux linkage over the fractional area, so that multiply this fractional area to this flux, differential flux d phi. So fractional area means what is the area of this particular cylindrical portion that we have considered is pi x square, and what is the total area of this conductor, that is pi r square. If we do the ratio, then we will get the ratio of how many times this portion is with respect to the whole conductor, that is x square by r square. Now we need to multiply this x square by r square to this x square by r square. Then finally my equation will be modified as mu naught I x cube divided by 2 pi r power 4, and this will be the final d phi x. Now we need flux linkage. In general, the flux linkage lambda is equals to n phi. Here number of turns in a transmission line is only 1. It is only one conductor, so that n value will be 1, and phi we have got recently. Now lambda is equals to this d phi x. Lambda is equals to mu naught I x cube by 2 pi r power 4. Now if we integrate this value, we will get the total internal flux linkage. This is the actual flux linkage that is going to happen within this fractional portion, but we need the total internal flux linkage of this conductor, so that integrate the value and you will get the total internal flux linkage. Integration of lambda x, and the limits are from where to where we need that flux linkage, from 0 to radius r. therefore 0 to r with respect to dx. Now I am integrating this 0 to r. Lambda x is equals to mu naught I x cube by 2 pi r power 4 dx. I am integrating with respect to dx means all the terms except x are constants here. Mu naught I divided by 2 pi r power 4 integration of 0 to r x cube dx. This will be equal to mu naught I by 2 pi r power 4 x power 4 by 4, and the limits are 0 to r. Now mu naught I by 2 pi r power 4, applying limits over here, r power 4 by 4 and r power 4 is cancelled, and finally we were remained with mu naught I by 8 pi. This is the total internal flux linkage of a conductor in a transmission line.